of the dispersion forces. HF is expected to have the weakest dispersion forces, while HI is expected to have the strongest dispersion forces, and that's the correct answer as well, 90%, which is really good. Okay, one more time, the dispersion forces depends on the polarizability, which depends on the number of electrons. For HF, we have only 10 electrons, and HCl is 18, and HBr is 36, and then I cannot remember, you should check. So how do we know that in HCl, for an example, has 18 electrons? Chlorine atomic number is 17, so it has 17 electrons plus 1 electron from hydrogen, so 1 plus 17 is 18, and that's how we get the total number of electrons. Yeah. So higher the number of electrons, more polarizable the molecule is. More polarizable the molecule, stronger the dispersion forces. That's it. All right. What questions, concerns, comments do we have at this point? Anything? Any questions? Okay. So if that is the case, we are okay with that. Let's do something different now, okay? But still dispersion forces. Here we go. So here's the molecular formula. Can you draw all the possible isomers for this? Few things I noticed. So again, we are chemists, okay? We are not magicians, so we cannot create or destroy atoms. I mean, magicians cannot do that either. Okay. Anyway, so if you drew things like this, okay. So I saw that some of you drew this. Okay. So if you drew this, you need to notice that we have 1, 2, 3, 4, 5, 6 carbon atoms here, but I only gave you 5 to work with, so therefore that's a no-go. Okay, so this is out because we have created carbon and hydrogen atoms here. On the other hand, if you drew this, okay, so you have 5 carbons, but each of these have 2 hydrogens bonded to it, meaning we only have 10 hydrogens in this molecule. Okay, I gave you 12, you destroyed 2 of them, so that's a no-go as well. Okay, you cannot create or destroy. Okay, therefore these structures are out. Okay, so only possible structures for these are, we can have 1, 2, 3, 4, 5. This is 1. Or you can have 1, 2, 3, 4, and then from one of them you have a thing sticking out. I call them umbrellas. Okay, I'll get to that later. Okay, or you can have 1, 2, 3. Instead of 1 sticking out, you can have 2 sticking out, like that. Okay, these are the only 3 possible structures or isomers for C5H12. Okay, A, B, and C. All right. What questions, concerns, comments do we have at this moment? Anything? Any questions, concerns, comments about this? Okay. Now, yes, we have a question. Can I have the microphone there, please? Remember your name is one more time.
Cece,
Cici, go ahead.
can you explain why each one would be correct?
Oh, yeah. So why each one be correct? Because we have 5 carbons and 12 hydrogens. That's the only reason. And how do I know it? I'm going to use this. Okay. So here's the first one. 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5 carbons. To fulfill the common bonding pattern, we are going to add carbon-hydrogen bonds to have 4 bonds around each of these carbons. If you count, you're going to see that they are going to have C5, 5 carbons, and 12 hydrogens. And then the other one I drew was this. Okay? Carbon, 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 carbon at the ends and bends. And then the common bonding pattern fulfilled by carbon-hydrogen bonds. Okay, that should be 3 for the terminals. And then this bend should have 2 more. And this one have only 1. So you're going to get 12 hydrogens. And the last one, we have 1, 2, 3, 4, and 5. So 1, 2, 3, 4 terminal carbons and 1 central carbon. And each of these terminal carbons will have 3 hydrogens bonded. Okay, 3 carbon hydrogen bonds like this. That means it's going to have 5 carbons and 12 hydrogens. Yeah? CC? Yes. We have another question behind you, Harshini. Remember your name is one more time.
No.
Kendall?
Yeah.
Kendall, go ahead.
How do you know to do those like shapes? How did you know to do that?
Oh, this, I did not do any shapes. I only drew like the line structures. And then these are the only possibilities. If you take even an hour and then, try to come up with them, these are the only 3 possibilities.
Okay.
I can do this like, instantly because I've been doing chemistry for close to 20 years now. It's a different story. So it's not impressive at all. Right?
Okay. Is
Yeah,
it the
but
same for other molecules? Like if you give us another one, we would like do kind of the same thing, like just make like up and down.
yeah,
up
you
and
can
down?
try. Yeah, yeah.
Okay, there's not like a specific thing that we need.
No,
Really?
yeah, some of them have more than 3, obviously. Okay, this molecule only has 3.
Okay.
Yeah, but
Thank
we will
you.
play with it. It's like, yeah. Any other questions, concerns, comments at this moment? All right, now here's the real question. I'm sorry, sir. All right, the real question here is, okay, out of these 3 molecules, these 3 isomers, okay, these 3 isomers or these 3 compounds will have very different boiling points. Here's the question. Which molecule, which isomer, A, B, or C, do you expect to have the highest boiling point? Go ahead. They will have 3 different boiling points. So, what was your answer again, William? Okay. All right. So, before I look at your answers, I want to tell you about my grandmother a little bit, okay? So, when my grandmother went out for any reason, any day, whether it is raining or whether it is sunny, whether it's a beautiful day, or okay, she would always carry not one but 2 umbrellas. Right? I asked the same question, why? Right? And I actually asked her why, one day, and what she told me was she's carrying her umbrellas not because of the weather, because she can use her umbrellas as barriers between her and the people, around her. Right? So, in these molecules, especially B and C, the things that are sticking out are like my grandmother's umbrellas. Okay, they are acting as barriers for the molecules to come closer to each other. Therefore, it reduces the surface area of contact. Okay, whenever you have less contact with other people, you have weaker interactions. Okay, therefore, your boiling point, melting point, density, viscosity, those stuff like that will go down. Okay, so one more time, let's go back to the molecules and then see the same thing again. Okay, so what we just explained was this, right? Between these 3 molecules, okay, in B and C, you have things sticking out. These are also known as branches coming out. Okay, these branches are like umbrellas of my grandmother. Okay, so they act as barriers for the molecules to come closer to each other. If the molecules cannot come closer, they cannot have stronger interactions. Okay, so as a result of that, these molecules B and C will have weaker attractive interactions or weaker intermolecular forces than A. So A has the strongest intermolecular forces, therefore highest boiling point, melting point, density, viscosity, and lower volatility and lower vapor pressure and so forth. Okay, so I'm going to actually, write that down. The keyword when you are handling a question like this, especially in free response, the key word is the surface area of contact. The surface area of contact, okay, is reduced due to, let me use the word branching, due to branching in B and C. Okay, So what does it do as a result of that? Therefore, as a result of that, the intermolecular forces, let me call it IMFs now, you know that now, intermolecular forces are weakened. It can be any type of intermolecular forces, can be dispersion, dipole, or hydrogen bonding. If you cannot get closer, then you cannot have strong interactions, okay? Are weakened in B and C, okay? As a result of that, boiling point, okay, will be lower, melting point will be lower, density would be lower. This is just, making a note. Density, viscosity, all those stuff will be lower. On the other hand, volatility will be higher because it easily goes to the gas phase now. And then vapor pressure will be lower, actually higher as well. Okay, why? It can easily go to the gas phase. You're going to find more of them in the gas phase. Therefore, you're going to have a higher vapor pressure in B and C compared to A. Especially C will have the lowest. Okay, because you have not just one umbrella, but two umbrellas sticking out, or two branches coming out, which are acting as barriers for the molecules to get closer to each other. All right. What questions, concerns, comments do we have? Again, the key word here is the surface area of contact. Okay, branching reduces it, and that weakens the intermolecular forces. I see a hand over there, Jacob. Thank you. Remember your name, Miss? What's your name, Miss? I'm sorry.
I'm Aiko.
I go.
Yeah.
Aiko, go ahead.
I was just asking, like, how do you know the surface area is smaller in certain like branches? Like, how do you know?
Whenever you have a branching coming out, it acts as a barrier for the molecules to get closer to each other.
Oh, so if it's branching, it just like automatically has a lower surface
Yes,
area?
exactly,
okay.
exactly. Compared to the one without one without branching. Wonder if I have any. Huh? All right. Any other questions, concerns, comments at this point? I have another question there, Jacob. Can you go there for a second? And actually, I'll show you the actual boiling points of these as well. These are the actual boiling points of normal pentane, isopentane, and then, neopentane. These are the names of them. Yes, sir. What's the name, sir?
Wyatt.
Wyatt, go ahead.
So like our last class, we went over how if they have more electrons,
Yeah.
you get more polarability, and then more polarability
Polarizability,
is stronger IMFs.
Yeah.
But wouldn't in this case all of them have the same amount of electrons?
Exactly. So that doesn't cut it, right?
Mm-hmm.
Yeah. So all of them are equally polarizable.
Mm-hmm.
But because of the branching in those molecules, the surface area of contact is reduced. Therefore, the intermolecular forces are weakened.
Okay.
Yeah. All right. Any other questions, concerns, comments? Okay. So if that is the case, yeah. So for example, okay. So the questions you can get is, okay, here are the boiling points of these molecules. How would you explain them? Okay, you're going to straight away bring up that term. Surface area of contact is reduced in say B compared to A. Okay, that's why it has weaker intermolecular forces. Weaker intermolecular forces means lower boiling point. That's why we have 28 as opposed to 36 in the middle one compared to the first one. All right. The key word is the surface area of contact. Right. So surface area. All right. So with that, let's try another one. Here we go. Now I'm giving you the data. Okay. I'm giving you hexane. By the way, hexane should have 14 hydrogens, not 12. It should be C6H14. To 980. Oh yeah, 90% answers no. Okay. Therefore, I'm going to close this question in 5, 4, 3, 2, and 1. All right. Okay. So here are our responses. Most of us say, okay, this is good. All right. It's a good starting point. At least most of us realize that benzene has stronger intermolecular forces. How do we know that? We see that benzene has a higher boiling point, meaning it should have overall strong intermolecular forces. And this is how we know that benzene has strong intermolecular forces. Why? The boiling point is higher. Okay, number one. All right, so that statement is correct. Okay, let's go to the second one. Dipole-dipole forces of benzene contribute to strong intermolecular forces. Okay, what do you guys think about that? Yeah, William? Thank you. So none of these molecules, okay, has dipole-dipole forces. Why? These are not polar molecules. These molecules only contain hydrogen and carbon, and we discussed the other day, if your molecule only contains hydrocarbons, okay, hydrogen and carbon, they are also known as hydrocarbons, they are non-polar for all government purposes. Remember we talked about that? Yeah? So these are non-polar molecules. Non-polar molecules do not have dipole-dipole forces. Please make a note there, okay? So option B is incorrect, right? And then option C, benzene is more polarizable as it has more electrons. Okay, no, right? If we count the electrons, hexane has 6 carbons, meaning you're going to get 36 electrons from that, 6 times 6. And then 12 hydrogens, that means 12 times 1 electrons from that. Altogether, we have 36 plus, actually, no, 14, right? Okay, 14 hydrogens means 14 electrons from them. So altogether, we have 50 electrons in hexane. On the other hand, in benzene, we have 6 carbons, 6 times 6, plus 6 hydrogens, 6 times 1. We only have 36 plus 6, which is 42. Is that right? Yeah? 42 electrons. Okay? So we have less electrons in benzene. Therefore, benzene is actually less polarizable than hexane. Okay? Now, let's go to option D. So option C is incorrect. Benzene has a greater surface area of contact. I like it. Anybody who selected option D as the correct answer, can you tell me why though? How do we know that benzene has a greater surface area of contact? Why? All right, can you have the microphone with William, please? William, thank you. Tell me why, William.
Benzene's flat like a pancake and can stack on top of each other. Hexane's like a cylinder, only there's only one very small point of contact.
Thank you. Are you saying that benzene reminds you of pancakes,
Yes.
William? Thank you. Me too. All right. Yeah, exactly. Now, get this. Here's the idea here. If you look at this carbon, okay, that carbon, any of this carbon has 1, 2, 3 electron domains around it. Okay, therefore, the electron domain geometry is trigonal planar. Whenever we have 3 electron domains, electron domain geometry is trigonal planar. Okay, and also all of these electron domains are bonding electron domains. They are in bonds. Therefore, what can you tell me about the molecular geometry? Thank you. It's also trigonal planar. Okay, all of these carbons are trigonal planar, meaning this molecule is flat. Okay, so when you have a flat molecule, let me try to do this with my papers over here. Okay, if you have flat molecules, look at this now. The flat molecules can stack on top of each other just like pancakes. They have a greater surface area of contact. Okay, on the other hand, something like hexane is like linear like that. Okay, they can only, at the best case, they can only get closer to each other like this. Okay, while benzene, it will always come closer to each other like this. We have a much greater surface area of contact in benzene compared to hexane. Okay, And that's why it has overall strong intermolecular forces, and that's why it has a higher boiling point. Okay, so what are the correct answers here? So benzene has overall strong intermolecular forces. And why that is the case? Because benzene has a greater surface area of contact due to his planar geometry. And also, benzene reminds me of pancake. That is also correct. All right. All right, I'll reopen the question. Okay. All right, please don't bring me pancakes next time, okay? I mean, it has happened to me before. So you don't have to bring pancakes to class. Okay. Um, all right. All right. What questions, concerns, comments do we have at this point? Anything? Any questions, concerns, comments? Okay. So one other thing, you can use your own analogies, okay, to remember things. All right. So it's easier for me to remember like benzene has a greater surface area of contact because it reminds me of pancakes. But you know, if you have another analogy, please use it. Same thing with the branching. Branching is like umbrellas of my grandmother. Okay, it helps me remember branching, or maybe my grandmother. I don't know, one way or the other. Okay, so if you have like nice analogies, all right, please use them. And also if you want to share with me, I mean, I would like to share with other people as well, so that we can help more people to remember these concepts. Okay, all right. Any other questions, concerns, comments before we do another one? Anything? All right. If that is the case, let's go to Google. All right. Oh, look at this. Give me a second. Here are our responses here. Beautiful. Nice. Okay. I'm going to clear my doodling. So I'm going to show you two isomers. Okay. One of the isomers have a higher boiling point than the other. What I want you to do is I want you to decide which one has a higher boiling point. Okay, if you feel like you want to use, ChatGPT, Copilot, Gemini, or Google, or whatever, okay, go ahead and do that. Okay, and then justify your answer. Here we go. This isomer, you know, these are cis and trans, right? So this is my cis. Why they are on the same side? This is my trans. Okay. Now, most of us clicked cis. Can somebody tell me why? I talked to William already, but I would like to speak to somebody else as well. William, I'm going to come back to you if I really need you, okay? All right. William is my last resort. All right. Now, who can tell me, okay, no, whatever the answer you choose, so why that is the correct answer? Okay, I hope that you use Google or AI. It doesn't matter. I mean, what does the AI say about this? Anybody? Thank you. Thank you. Can I have the microphone there, please? Remember your name is one more time. Ruby, go ahead.
The cis isomer is more has a higher boiling point because it's polar, and the trans one is non-polar.
Spot on. Spot on. Exactly the point. All right. So here's the thing. So both of them, like Ruby said, has 2 carbons, 2 hydrogens, and 2 Cl2, 2 Cl atoms. Okay, meaning if you drew the a bar chart for the intermolecular force strength, okay, so I'm gonna have, I mean, everybody should try to do this actually. So let's have intermolecular force strength. All right, strength on the y-axis, and the isomer over here on the x-axis, trans and cis. Okay, so they both have, say, the same number and types of atoms because they both have the same chemical formula, meaning the dispersion forces will be comparable in both cases. So if D is for dispersion, both of them will have uh, um, no, similar dispersion forces. However, on top of dispersion forces in the cis isomer, because we know we have two dipole moments going this way in the cis isomer, meaning you have a net dipole moment that goes in this direction of the chlorines like that. Okay. Therefore, on top of the dispersion forces, the cis isomer has dipole-dipole forces as well. Okay. So because of that, overall, the cis isomer has stronger intermolecular forces. Therefore, we can expect that to have a higher boiling point. Okay, this is called a bar chart for the intermolecular forces. All right. What questions, concerns, comments do we have at this moment? Anything? Any questions, concerns, comments? Do we have? No. Okay. Do we have any questions? Okay. All right. So now, why did I bring this up? Yes, we have talked about dipole-dipole forces before, but I want to revisit that, and this is the segue to discuss, rediscuss dipole-dipole forces. Okay. Yeah. Yes. Thank you. Where is it? Kimberly? Yes.
Okay, so the cis one, it's stronger because they're all pointing like the same way, and the other one is
It's
pointing
stronger because you
opposite.
have dipole-dipole contribution in the cis conformation.
So it doesn't matter like where the arrows are pointing, or it doesn't matter.
So you mean the dipole-dipole in
Yeah.
dipole? Yeah, I mean, so the trans is non-polar. Why? The bond dipole moments cancel
Going
each other
opposite.
out.
Yeah.
Yeah, so that's the net dipole moment is 0 for a
Okay.
trans. Okay, for cis, there's a net dipole moment going towards the direction of chlorine. Therefore, it's a polar molecule. Polar molecules has dipole-dipole forces on top of dispersion forces.
Okay.
Okay?
Okay, makes
That's
sense.
why overall you can have strong intermolecular forces in cis, therefore higher boiling point, melting point, density, viscosity, and so forth.
Okay, thank you.
Yeah, wonderful. All right. Any other questions, concerns, comments? Okay. So I think just to elaborate a little bit on Kimball's question. Okay. So in trans, we have two dipole moments going in opposite direction. They are equal in magnitude. When you add them up, they add up to 0. Therefore, the net dipole moment is 0 for the trans. Okay. For the cis isomer, the net dipole moment is not 0. So therefore, it's a polar molecule. Not 0. Therefore, it's polar, and that's why you can have dipole-dipole forces. Okay. All right. So with that, let's talk about dipole-dipole forces one more time. Okay. So dipole-dipole forces always interact from head to tail. That's why they are called highly directional. Okay. It's always go from head to tail. Okay. And then for you to have dipole-dipole forces, you need to have a polar molecule. And also remember what we did towards the end of the class on Tuesday. The dipole-dipole force strength depends on the molecular polarity or the net dipole moment strength. Okay, higher the molecular polarity or higher the net dipole moment, stronger the dipole-dipole forces. Just like dispersion force strength depended on the polarizability, okay, dipole-dipole force strength depends on the molecular polarity. All right, this is in our notes already. So keeping that in mind, this is what I want you to do. Here are some molecules. I want you to arrange them from weakest dipole-dipole forces at the top to strongest dipole-dipole forces at the bottom. Go ahead. You will probably need the electronegativity values for these. I'll give those to you, the ones I can remember at least. Okay. So hydrogen is 2.1. Fluorine is 4.0. Chlorine is 3.0. 3.16. Yeah. 3. Okay. I think in the polling scale, the table I gave it was labeled as 3.0, William. So I feel like in an exam, I mean, if you're given the electronegativity values, you will be given as 3.3.0, but yeah, it might be 3.16. Can you let me know the bromine though? Yeah, I think it's 2.8 or something like that okay, that's okay. Yeah, something. All right, I think we have close to 90%. Yeah, I have more than 90% actually, okay. So I'm going to close this question in 5, 4, 3, 2, and 1. All right. And the most popular response is this. HBr has the weakest dipole-dipole forces. HF has the strongest. I agree with you. And then if I can get you used to drawing the dipole moments, there's only one bond here. Therefore, the net dipole moment is the dipole moment of that one bond. So HF has the greatest electronegativity difference, right? 2.1 for hydrogen. Fluorine is 4.0. So the electronegativity difference is 1.9 for HF. Therefore, it will have the greatest dipole moment. Okay. And then HCl, chlorine is 3, hydrogen is 2.1, the difference is 0.9, bless you. Okay. Therefore, HCl dipole moment will be smaller than that of HF. But in HBr, the electronegativity difference is smaller than that of HCl as well, 2.8 minus 2.1, which is only 0.7. Therefore, it will have the weakest dipole moment. Okay, so and we know the dipole force strength over here, okay, depends on the molecular polarity. HF has the greatest molecular polarity, therefore strongest dipole-dipole forces, and HBr has the lowest molecular polarity, therefore it's going to have the weakest dipole-dipole forces. Okay, and that's the idea behind the most popular answer here. All right, almost 90%. All right. What questions, concerns, comments do we have at this moment? Anything? Any questions, concerns, comments? Right. And this is all we need to know about dipole-dipole forces. Wonderful. All right. And with that, I'm going to clear my doodling. And let's try this. Okay. So again, for this, feel free to use any AI you want. Okay, Google or AI or Copilot, whatever you. All right, so I'm gonna close this question in 5, 4, 3, 2, and 1. All right, so can somebody tell me the boiling point of? Should I do it this way? Yeah, that's okay. Yeah, so again, okay. All right. So negative 66. Can you check the units again? 66 Fahrenheit. So Celsius. Okay. And HF is what? 19.5. That's the same as what William got before. 19.5 Celsius. Okay. HCl. Did you say negative 85? Okay. Negative 85 Celsius. Okay. All right, this looks better. I don't know if that's actually, but anyway, this looks better. Thank you. Okay, so these are the actual, the boiling points values we got from internet. Okay, so these are these are fine. Okay, we can run with them. Okay, now one other question: what value is bigger, negative 66 or negative 85? Negative 66 is bigger. Right? Okay. So keep that in mind. And therefore, if you drew the bar chart, let's do that. Okay. So I'm going to have intermolecular force strength on the y-axis. Okay. This is IMF strength, and then I have HF, HCl, and HBr. Okay, so what we know is based on the boiling points, okay, we have the strongest intermolecular forces in HF. It's pretty strong actually. All the others are negative. Okay, and then HBr. Okay, then HCl has the weakest overall intermolecular forces. Okay, now let's think about why this is the case. So HF has, let's count the electrons, okay, has 10 electrons. Fluorine is 9, hydrogen is 1, 10. Chlorine, HCl has 18. Chlorine is 17. 17 plus 1 from hydrogen is 18. And HBr is 36. Bromine is 35. Hydrogen is 1. Therefore, altogether we have 36 electrons here. Okay. Therefore, the dispersion forces wise, let's call dispersion forces D. HF has the weakest dispersion forces, and then HCl has a little bit stronger dispersion forces than HF, but HBr has the most number of electrons, therefore it has the strongest dispersion forces. Okay, and then what is D? D stands for dispersion. Dispersion forces. Okay, I'll write it out. That's okay. Forces. Okay. Now, other type of intermolecular forces. Okay, now we have dipole-dipole. HF is the most polar molecule. Therefore, let me use a different color. So HF has stronger dipole-dipole forces. Okay, let's say that it has the strongest dipole-dipole forces. Okay, then HCl, right? And HBr has the weakest dipole-dipole force. This is the last question we did. Okay, now this doesn't explain why HF has, overall strong intermolecular forces. What are we missing? Anybody? What is missing? Thank you. Okay. On top of dispersion and dipole-dipole, in HF, we have what we call hydrogen bonding forces. Okay. So HB stands for hydrogen bonding forces. H bonding forces. That's the last type of intermolecular forces we learned today. Okay. Now, just for the completion, let me write the key for the DD as well. DD stands for dipole-dipole. Dipole. Dipole. Dipole forces. Okay. Now, just to complete our notes, okay, I need to go back to my notebook for a second. Okay. Here we go. This is what we have in our notes. Oh, I mean, how to clear doodle for a second. Okay. So when it comes to hydrogen bonding forces, here's what we need to do. Hydrogen bonding forces only occurs when we have hydrogen covalently bonded to nitrogen, oxygen, or fluorine. Okay, if you do not have hydrogen covalently bonded to nitrogen, oxygen, or fluorine, we do not have hydrogen bonding interactions. Okay, so please keep that in mind. And then that's the first requirement for that. And then hydrogen is to be sandwiched between any of these elements when it comes to a hydrogen bonding interaction. Okay. All right. So let me actually show you some hydrogen bonding examples, like illustrations, and then we will play with that. Okay. So here's an example. Okay, in HF, this hydrogen can interact with the fluorine of the adjacent HF molecule using hydrogen bonding interactions. Okay, so now you can see when that happens, our hydrogen atom here is going to get sandwiched between two fluorine atoms. All right, so this is an example of hydrogen bonding interactions. And also, I'm going to show you another example. It doesn't have to be the same molecule. Okay, so only requirement is we need to have hydrogen covalently bonded to nitrogen, oxygen, or fluorine. In this case, we have hydrogen bonded to nitrogen, and that can interact with the oxygen of a carbonyl group like this, okay, via hydrogen bonding interactions. Okay, so here's the point here, in case you didn't say it. This oxygen over here does not have hydrogen covalently bonded to it. But that is fine. Why? Because the hydrogen that is interacting with that has a nitrogen atom covalently bonded to it. Therefore, it is fine. Okay. As long as we have a hydrogen from anywhere covalently bonded to nitrogen, oxygen, or fluorine, okay, that can participate in hydrogen bonding interactions. Okay. All right. Now, the other thing I want to point out is, okay, so, I mean, you can have hydrogen bonding interactions with, different molecules like this, okay, as shown here. And also, if somebody drew something like this, let's say that I'm going to draw something like this. We have, no, not that. I'm sorry. That's not what I wanted to draw. Okay. Let's say that I have a water molecule over here. Okay. If somebody drew a water molecule, and then drew dotted lines, 3 dots to indicate interacting with this hydrogen over here. Is this hydrogen bonding interactions? Everybody, can you think about this? So this, I mean, what I'm indicating over here, all right? Can you write on your whiteboards, is this hydrogen bonding interactions or not? Go ahead. Yes or no? That's all I'm asking. Okay. That water molecule and that, 3 dotted lines interacting with that hydrogen, is it considered as hydrogen bonding forces? Can I see the answer on your whiteboards, miss, please? Everybody, can you please write your answer on the whiteboard? I am going to have a question like this on your exam tomorrow. All right, exam 3A. So let's think about this now so that everybody can get 100% for that question. All right. Can I see your whiteboards, everybody? I want to see your whiteboards. I see no, 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 yes, no, no, mainly no. Why? Why isn't it hydrogen bonding? Can somebody tell me? Why? Was that miss? Why isn't it hydrogen bonding? You can shout a little bit. Yeah? Anybody? I mean, you know the answer. I know you know the answer. Happy Halloween. Thank you. Okay. Anybody? I know you know it. You just didn't tell me. Okay. Why don't we consider that interaction as hydrogen bonding? Anybody? Yes. Thank you. You want me to name, miss?
Kendall,
Kendall, go ahead.
because there's not a hydrogen in the middle.
There is hydrogen there.
Where?
Oh,
Okay, it's not bonded in the middle.
thank you. It is not bonded to nitrogen, oxygen, or fluorine. It is bonded to a carbon. You see that? There is this hydrogen over here. This hydrogen is covalently bonded to a carbon, which is not nitrogen, oxygen, or fluorine. And this is why this is not considered as hydrogen bonding interactions. Okay, please keep that in mind. Yeah? All right. What questions, concerns, comments do we have? Okay. So just to summarize at this point, we have talked about all 3 types of intermolecular forces. Okay. Dispersion, dipole, and hydrogen bonding forces. Here's what we need to remember. Anything that you can think of, any molecule, atom, or a polar or non-polar molecule will have electrons, therefore they will be polarizable. As a result of that, any molecule that you can think of will have dispersion forces. Okay? So on top of that, if your molecule is polar, meaning if your molecule has a net dipole moment, on top of dispersion forces, they will have dipole forces as well. Okay? And on top of being polar, if you have hydrogen covalently bonded to nitrogen, oxygen, or fluorine in that polar molecule, okay, like these 2 guys over here, On top of dispersion and dipole-dipole, they will have hydrogen bonding forces as well. Okay, so this slide summarizes all the possible intermolecular forces. Okay, all right. What questions, concerns, comments do we have at this moment? Anything? Any questions, concerns, comments? All right. Now, if that is the case, we are done with our intermolecular forces discussion. I'll just briefly mention this because people ask me about the strength of intermolecular forces. Okay, compared to covalent bonds, intermolecular forces are very weak. Okay, covalent bond energy ranges from 200 to 1000 kilojoules per mole, while intermolecular forces can only go up to 40 kilojoules per mole. Okay, and within the intermolecular forces, dispersion forces can range from 0.05 to 40, dipole-dipole forces 5 to 40, and hydrogen bonding is 10 to 40 kilojoules per mole. Okay, now here's the thing to remember. We say that hydrogen bonding forces are the strongest intermolecular forces. Why? Because the weakest of hydrogen bonding is pretty strong compared to weakest of dispersion and dipole-dipole. That's the only reason. But here's the thing that you need to remember. Even the dispersion forces can be as strong as or even stronger than hydrogen bonding forces if you have enough electrons. Okay, I'll give you an example really quickly in my notes, I think. No, I mean, yeah, somewhere else. Okay, that's okay. All right, so I can do this in my notes. I'll use a new page. Okay, so earlier we saw HCl and HBr, right? So HCl is more polar than HBr. Okay, HCl has only 18 electrons and HBr had 36 electrons. Okay, however, HBr has overall stronger intermolecular forces than HCl. This just remind us. Okay, why this is the case? Even though the HBr is less polar, their dispersion forces are much stronger. Okay, here's the dispersion forces of HCl, and then you have dipole-dipole. Okay, so you see that if you have enough electrons, the nonpolar molecules, relatively nonpolar molecules, can have even stronger dispersion forces. Okay, and there's a fake rule for this as well, and that rule is called 15 electron rule. Yeah, I'm going to mention that really quickly because that might come in handy. Okay, so 15 electron rule says if the nonpolar molecule has 15 or more electrons than the polar molecule, then the dispersion forces in the nonpolar molecule may outweigh the dipole contribution in the polar molecule. Okay, this is a fake rule, but it helps us sometimes when we have to predict the explain the relative melting points or boiling points. All right, I just want to mention that because there had been instances where this has been useful. Okay, so yeah, then again, okay, the point is even the dispersion forces can be as strong as hydrogen bonding forces or dipole forces if you have enough electrons. So that's why we talked about that. All right, with that, for the road, I think we'll do one more question. Okay, here are some molecules. Can you rank them in the order of let's say, decreasing vapor pressure, highest vapor pressure at the top and lowest vapor pressure at the bottom. Okay. By the way, vapor pressure will be lower with stronger intermolecular forces. Percent answers. So for the sake of time, okay, I'm going to really quickly mention this, okay? So C3H8 is a non-polar molecule, therefore it will only have dispersion forces. C2H6O is a polar molecule with hydrogen covalently bonded to oxygen, therefore it will have dispersion, dipole-dipole, and hydrogen bonding. Okay. On the other hand, C2H4O is a polar molecule, but it doesn't have hydrogen bonding capability, but therefore it should only have dispersion and dipole-dipole. Okay. Because you have all three in this, it will have the strongest intermolecular forces, meaning lowest vapor pressure. Because this has only dispersion forces, it will have the weakest intermolecular forces overall, therefore highest vapor pressure. All right, I think that's it. That's the one for the road. All right, here's the attendance code for today. Bye everybody. Happy Halloween.